Welcome back to chapter 7 here as we add a couple more functions into your library that then you can use to describe or to model real life and to do calculus on. Doing calculus meaning taking a derivative and finding the instantaneous rate of change, or integrating that function and adding up little bits of area or volume or little bits of distance. Okay, so anyway, let's get going with the exponential function here. E to the x and its derivatives. And in the previous video, you saw the graph of this function. You have to know what it looks like. This is a function you should know, be able to draw. Now, what's curious about it is the derivative of e to the x here, okay? If you take the right up here, if y is equal to e to the x, the derivative also turns out to be e to the x. All right? So the function and its derivative are the same, which creates a lot of interesting properties. Okay, what if I said y was equal to this derivative here? Not derivative, but I integrated it. What's the antiderivative of it? Well, I'm going to give it to you here. I'm going to say it's e to the x plus c. So the derivative and the antiderivative are the same. Now let's check that. Let's check that that works, right? I know that if I take the derivative of this antiderivative, I better get back to that. Is that true? Let's see. Well, dy dx is equal to, what's the derivative of e to the x? Oh, I was told it was e to the x. Derivative of c is 0. So yes, this guy, okay, the derivative and the antiderivative of e to the x are the same function, which is kind of unusual. Okay, let's look at another problem over here. And this, remember, we talked about the properties of exponents, but let's just, what is this e to the natural log base 2 here? Notice these are inverse functions, right? So if I put in 2 through the log function, I get an output, and I put it through the inverse function, I get back to what I started with. So this is really going to be equal to 2 to the x, right? What's the derivative of that? I'm going to say dy dx is equal to what? Well, actually, before we do that, let's just rewrite this thing. This property of exponents tells us this is e to the natural log of 2 times x, okay? These are multiplied by each other. Now we can do a little chain rule action. What is dy dx? Well, dy dx is equal to, let me remind you again. We're going to remind you the chain rule. We're going to use this chapter as an opportunity to review a lot of the things we've learned in calculus. Not everything, but okay. The inside function is this, right? What's the derivative of natural log of 2? Is just a constant times x. So the derivative of a constant times x is just the constant. So I'd bring the natural log of 2 out front. What's the derivative of the outside function? Well, we know that the derivative of e is just e to the natural log base 2 of x. So that's it. This is the derivative of that function of 2 to the x. If you give me an exponent of any base, I can also take that derivative. Well, let's clean this up a little bit. What's e to the ln of 2? Let's go back to, that's really going to be e to the ln of 2 to the x power, ln of 2. What's this right here? That is just 2. So this is going to be 2. That's just 2, right? 2 to the x ln of 2, dy dx. So these are important results here. This is important result. These are the most important. This could also, from our derivation we just did, you might see that if I gave you this pair, let's do this. If I said y was equal to a to the x, a could be any number. I use 2 here, but it could be any base number. dy dx is now equal to the natural log of a times a to the x. Okay. But this is an interesting derivation, okay? Interesting derivation, nice to know. These guys are very important, though. We're going to basically work with these results, and the next couple of problems, we're just going to work problems that you've done before, but now we're introducing a new function, e to the x. Okay, as I said before, now we've just got a different kind of function here. Let's start here to go back to black. Right, remind you about the chain rule. What's the derivative? I've got an outside function. Outside function's e to the x. And an inside function is fx squared. What's the derivative of the inside function? Well, that's just going to be 15x squared, right, times the derivative of the outside function. It's going to be e to the inside. Okay, that is a multiplication sign there. Okay, one may be a little bit harder. How about this number 2? I don't think it's really any harder. Let's see. dy dx equals to, what's the derivative of the, we'll do inside in red. The derivative of the inside function here is just, that's just e to the x. E to the x times the derivative of the outside function, which is going to be the cosine evaluated at the inside function. That's e to the x. That's the derivative of that part. Well, now we got an addition. What's the derivative of this? Here, once again, we've got an inside function, right? The outside function is e to the x. The inside function is sine of x. What's the derivative of the inside function? Well, that's just the cosine of x, right? You know those pairs. What's the derivative of the outside function? It's e to the whatever the inside is, which is sine of x. Sine of x, okay? There you go. Okay, so chain rule. What a great opportunity to review the chain rule. Okay, let's see what else we got. Ooh, how about this? What's this a review of? Now I don't have an explicit function, do I? I don't have y as a function of x. I have an implicit function. I have an implicit function, and it's implied that y is a function of x here, right? Let's put that in here. And now I've got to take the derivative of both sides. Let's see if I can do that. I'm gonna do what? Take the derivative of both sides. Derivative of that with respect to x. Derivative of this with respect to x. Okay, so I'm working on the left side here, and I've got the inside function is x squared y. Well, that's going to be a product rule, right? That's going to be 2x. The derivative of x squared is 2x times y plus x squared. What's the derivative of y? That's just y primed. That is the derivative of the inside of this guy. What's the derivative of the outside? Well, it's just e evaluated at the inside is equal to, okay, we can do the left side. It's just a addition. That's 1 plus y primed. What do I do now? I bring all my y primes to one side. Well, I want to do that. We'll do it to 2xy e to the x squared y plus x squared y primed x squared y, 1 plus y prime. Okay, I'm going to bring all these guys together. I think I'm going to say y primed. Oh, I'll do it. We'll do it in a little more. X squared e to the x squared y. Y primed is equal to what's left on the left-hand side? 2x y e to the x squared y minus 1. Okay. So y primed, I can factor that out, right? 1 plus x squared e to the x squared y is equal to this guy, huh? And then y primed is just going to be equal to 2x y e to the x squared y. That's 1. Bringing that down, divided by this guy, bringing it over, right? 1 plus x e to the x. Okay. Now you've done that before. Implicit differentiation. You know that this gives me, if you plug in, give me any x and y on the original function. Give me any x and y. So if I put in what? X equal to 0, would that work? X equal to 0, y equal to 1. I'm seeing that works. 1 is equal to 1. If I take that point is on that curve, I can also plug it into here, and this will tell me the slope of the tangent line at that point. Okay, let's see what else we got. What other reviews we have using this function? Oh, let's see here. Oh, here we go. We got an integral. Okay. Well, I know what the antiderivative of e to the x is now. So and again, what's this a review of? Looks like it's a review of substitution to me. Oh yeah, I see that the derivative of x squared is x. That's how substitution works, right? I see the derivative. There it is. That's the derivative. Okay. So what do? I say u is equal to minus x squared. What is then du? Du dx, we'll put it over this way, is equal to minus 2x, which then implies that du, remember this is just a ratio, change in y, or change in u over the change in x, du equals minus 2x dx, or du minus du over 2 is equal to x dx. There's what I'd call the old knockout blow right here is equal to that times that. So now my whole integral, I'm going to substitute back in. X dx is going to be minus du over 2, and then this guy becomes e to the u. Okay, now as I like to, let's do a substitute of limits too. This is x equal to 0, that's x equal to 1. This needs to be u equal to, when x is equal to 0, x equals 0, u equals 0. When x is equal to 1, put a 1 in here, u is equal to minus 1. So this is going to go from u equal to 0 to u equal to minus 1. Clean this thing up a little bit. Another little cleanup step. Take the minus 1 over u, u to the minus 1, e to the u. Yeah. Okay. Clean that up. Well, what's the antiderivative of e to the u? That's why we're talking about this, right? We're talking about this because we got a new function. We know what that antiderivative is. It's just e to the u from minus 1 to 0. Minus 1 half out front. And I'm going to keep this minus 1/2 e to the minus 1 minus e to the 0. Now, e to the 0, you know, a lot of times in the past, when you put in a 0 into the function, it becomes 0, but not the exponential function, right? When you put e to the 0, this is 1. All right? So this whole thing becomes equal to minus 1/2 e to the minus 1 minus 1. Or you could rewrite that. Notice this in here, that's a negative number. E to the minus 1 is less than 1. Again, it's nice to have this curve in your head. This is e to the u. You can have that. That's 1. We put in a 0, you get 1. You put in a minus 1, it's less than that. So you could also rewrite this as 1/2 1 minus e to the minus 1. Okay? All right, so we introduced a new function. The new function was this function here, the exponential function. We saw its derivative is equal to the function back. The antiderivative also equal to e to the u. And we did a little review of integration technique of substitution. We did implicit differentiation, and we reviewed the chain rule. You know, we could do volumes, we could do application of derivatives, we could find tangent lines, you name it. We got a new function, we can do calculus with it. Okay, we're going to move on to a new function now. Let's throw in the log function. See you soon.